Hello, this video is for Chapter 7, Sampling Distributions. In future chapters, we will be learning inferential statistics. In those chapters, we will be using random samples to make estimates about population proportions and population means. That's random samples right there. And to do this well, we need to learn the sampling distribution for two random variables. One of them is a new one for us. It's called the sample proportion, and we use a p hat to represent that. And the other one is the sample mean, which is x bar, something we're familiar with from back in Chapter 3. In section 7.1 and 7.2, we're going to focus our attention on the sample proportion, and then we'll come back and look at the sample mean in 7.3 and 7.4. And in this video and this notes packet, we're looking at 7.1 and 7.2 combined. So you would want to complete this whole section of notes before you started either section of the homework, because there is kind of a mixture of the concepts from those two sections kind of spread out through this portion of the notes. All right, so let's define some things. So our first note is that we're going to let a lowercase p represent the population proportion. And then, as we mentioned just right up there above, we're going to let p hat be the sample proportion. So this is kind of, for the mean, this would be x bar would be a sample mean, and mu would be the population mean. So these are the symbols that kind of correspond to that when you're talking about proportions. And the second note is that when you're calculating a p hat, that's going to be x over n, where x represents the number of data values with the desired attribute. And when we talk about a data value having a desired attribute, we're really saying it's a success. So the x in the x over n is the number of successes, and then n is our sample size. So we're going to be switching our focus from the number of successes, which we looked at a lot in 5.5, and start looking at the proportion of successes in this section and beyond. All right, so let's look at an example to start to get a feel for this. Suppose that it's known that 52.2% of Americans approve of the job that the president is doing. If we take a random sample of 614 Americans, what percentage of the sample should we expect to approve of the job the president is doing? All right, so the key here is that it's a random sample and the size is fairly large. And if you have a fairly large random sample, it should be representative. And if it's representative, then sample values should come out fairly close to the population value. So when they say that it's known that 52.2% of Americans approve of the job the president's doing, basically what they're telling us right there is that the true probability of that trait is 0.522 in the population. And then when they say what proportion would we get in the sample, they're asking us about p hat. But if it's a representative sample, we should expect a sample proportion to come up pretty close to the population proportion. So I'd like to say 52.2% will be the percentage of successes in our sample. But the thing that we have to remember is that when we have a random sample, there's random variation in there, so you can't expect it to come out exactly like that. So I think it would be better if we put the word either about or approximately out front. So I think it would be about 52.2%. So when you start thinking about that word about, I'm saying random variation is going to cause some sampling error. So we'd like to think about how much sampling error. And so typically you would think that a random variable would come out within a couple standard deviations of its mean. So if I really want to answer this question well, I need to think about a few things. What is the mean of the possible sample values I can get? So really what I'm asking is, what is the mean of the possible p hats? And then I also want to know how much I might miss by, and that's kind of controlled by how spread out those p hats are. So I'd like to know what is the standard deviation of those sample values. So I want to figure out the standard deviation of p hat. And then to really be able to do a good job with this, I'd like to talk about the probability of being within a certain distance. So I'm not going to necessarily get the 52.2%, that's the population value. I might miss by a bit. And so somebody might say, what's the probability you'll be within 2% of the right answer or something? And to start answering probability questions, I need to know what is the shape of the distribution of all the possible sample values. So what kind of distribution does p hat have is the third piece of information that we're after. So by the time we're done with this packet on 7172, we'll have come up with a formula for the mean of the p-hats, a standard deviation for the p-hat formula, and we'll come up with a criteria for helping us figure out the shape of the distribution of the possible sample values. So let me just do one more definition here, and then we'll look at some of this on the computer. So a statistic is a value that's obtained from a sample that's used to estimate a population quantity, and the population quantity we're trying to estimate is referred to as a parameter. Worth a quick note that we're taking a class called statistics, not a class called parameters, and that's because the main goal of this class is to use a sample value to estimate a population quantity, but that sample value is referred to as a statistic, so you could say we use statistics to estimate population parameters. So that's mainly what the course is about. And the statistic is also known as a point estimate. So in this section, we'll be examining using the sample proportion as a point estimate for the population proportion. So we're going to get into some other definitions and examples, but before we do that, I want to go ahead and show you something on the computer that kind of gives us some hint as to how these three questions are going to turn out. And after we kind of get a hint from that from the computer, then we'll come back, we'll do a couple definitions, and we'll try and work out formulas for these and kind of a theory for what shape we'll get out of those. All right, so here comes the tech demo, and then we'll be back to lecture. Alright, so let's go ahead and look at an application that will illustrate what's going on in this approval rating problem. So I want to set up the simulation. They said we're going to sample 614 Americans, so I'll put 614 for N. And they said that the true proportion of Americans that approved the job the president was doing was 0.522, so I'm going to enter that for the probability of success P, and that P represents the true proportion. And I just want to show you what happens with our sample proportions when we take a sample of this size from a population where this is the population proportion. So if I run it once, when I click that, it's going to simulate asking 614 people if they approve of the job the president's doing from a population where this is the true percentage who would say yes to that. So I click run once, and I get 316 successes out of 614 people sampled. And as a decimal, that's 0.5147. So notice that's pretty close to 0.522, and we said that if we took a random sample from this population of this size, our proportion or percentage of successes should be about the same as this 52.2%, and it's fairly close. This little kind of pinkish line right there represents the 0.522, and that little notch right there is this 5147. So you might think if I click run again, since it's p-hat, I'd get the same thing, but we have to remember it's a random sample, so I'll get a brand new sample, and people, due to random variation, might answer the questions a little differently. So I run it again, a different sample of 614 people. This time 325 said yes to the question. That gives us a sample proportion, or p-hat, of 0.5293, and there it is right here. So the thing to notice so far is that the value of p-hat varies depending on chance. We're taking a random sample, and depending on who we end up selecting, we get different answers. So we should think of this value of the sample proportion, or p-hat, as a random variable, because when we do it, we keep getting different values. The other thing I want you to notice is that those values are kind of scattered around, and so far none of them have been equal to this 0.522. So I'm going to keep doing that, 5049, 5114, and I'm just watching to see if I ever get 0.522. There's 5228, that's very close. So 321 successes gave us something just a tiny bit bigger than that, and you can see that right there on our graph. So let's do a few more of those. There's the 5228 again. I want to see if I can get something on the lower end. There's 5212, very close to this and a little smaller, and that's just on the other side of the pink line. And that was 320 successes. So 320 successes gave us a value of p-hat that was smaller than this, and 321 successes gave us a value that was bigger than this for p hat. And the number of successes has to be a whole number, so it actually looks like it's impossible that we would get a p hat here that's equal to the population proportion, and that is typical for these sort of things. Alright, so while our values never have been our values of p hat have never been exactly equal to this, several of them have been close. Some of them a little bit far away, and some to the left and some to the right. So I want to start seeing if there's any patterns in this, so I'm going to click automatic to start generating these faster and just start seeing what happens. So we're getting into the thousands of times we've done this. We've got lots and lots of p hats. So, and based on what we saw before, none of them are equal to the 0.522. Some are to the left, some are to the right. And when you have multiple values of p hat, it starts making sense to think about, well, what is the mean of those p hats? In symbols, that would be mu of p hat. And it looks like that's settling in on a number, and it looks like that number might be p. So we'll investigate that on the next page of the notes to see if that is indeed the formula. But based on what we're seeing here, it looks like the mean of the p hats might be equal to p. And the standard deviation of the p hats also seem to be settling in on some number, 0.0201, and then the next two digits aren't quite settled. But it'll be worth investigating, is there a formula for the standard deviation of p hat also, because it seems like that is converging to some number. And then the shape of the p hats is actually taking on a very nice bell shape. So perhaps the p hats will end up being normally distributed since they're taking on a bell shape. And we'll investigate that in the coming pages too, but it looks like there's hope for that. So the few things we want to see from this demo, one of them is that every time you do p hat, you tend to get something a little bit different. Sometimes too low, sometimes too high, tends to never be right. The mean of the p hat seems to be settling in on the true value of p, which is interesting because not a single one of the p hats equals p, but the average of all those p hats is p. And the standard deviation seems to be settling in on a number as well, so we want to come up with formulas that will predict this. And it seems like we're getting a bell shape. And it turns out that you don't always get a bell shape, so we're going to need to figure out when do we get this and when don't we. Alright, so hopefully that gives us a little insight into what we're trying to figure out, and we'll investigate that some more on the next page. Alright, so in that video demonstration, I kept getting different values of the sample proportion, and we were noticing that while they were fairly close to 52.2%, they were a little different. And that difference between our sample proportion and the actual population value of 0.522 is referred to as sampling error. So let's define that real quick. The error resulting from using a sample instead of a census when you're estimating a population quantity is known as sampling error. So if our true value is 0.522 and then we get a p hat of 0.542, then we're off by about 0.02, and that would be the sampling error. And our goal in statistics is to try and minimize this sampling error and to try and get a handle on how much of it there is. And we do that by trying to answer these three questions. What's the mean of the possible sample values? What's the standard deviation of them? And what's the distribution of them? And we can kind of combine all of that we're after into one by saying we're looking for the sampling distribution of proportions. And that is the probability distribution for all the different values of the sample proportion. And when we start talking about the distribution of a variable, in this case the sample proportion, we're making the claim there that that variable, or that value is a variable. So the sample proportion really is a random variable. And we did see that in the video demonstration or the computer demonstration, because every time we would get a different sample, we would tend to get a different value for the sample proportion. So the value of p hat really did depend on chance, which is what makes it a random variable. So now we're going to try and completely describe that random variable, and we'll get started on that task on the next page. Alright, so let's start trying to work on the formulas we need to come at a probability distribution for p hat through an example. So studies have shown that 40% of all video game players are female. Suppose that we randomly select 187 video game players. What is the probability that the sample proportion of females will be exactly equal to the population proportion of females? So before we get started on answering that question, let's note some of the things they gave us in here. We're going to randomly select 187 video game players. So that means our sample size is 187. And it says studies have shown that 40% of all video game players are female. And as you look through, we're going to keep focusing on the percentage of female players. So this is the true value from the population. So that's P. So that's 0.40. And if we're going to write down N and P, we might as well get Q at the same time. So Q is 1 minus P, so 1 minus 0.40 would be 0.60. And that makes sense. If 40% of the players are female, then the other 60% are male. So what is the probability that the sample proportion of females will be exactly equal to the population proportion of females? So first let's just translate that. What is the probability that? That would be P of something. What's the probability that the sample proportion, we just learned that the symbol for sample proportion is P hat. And what's the probability that P hat will be exactly equal, not approximately equal, but exactly equal to the population proportion, which is P. And then we know what P is, so we could say that this question is really what's the probability that P hat will be equal to 0.40. And one of the things that we saw in the computer demo on the previous page is that we didn't get any P hats that were exactly equal to the population proportion. And that's typically the case. So you kind of expect that you're not going to ever hit it right on the nose. So when somebody asks you what's the probability that P hat will be equal to P, we've kind of seen from the tech demo that just doesn't happen. So we'll usually say that it's 0. There are some kind of weird cases now and then where it is possible, but even then, the probability of getting it exactly right tends to be pretty low. So usually the probability of getting the right answer is 0. When it's not 0, it's close. So from here on out, when somebody asks us what's the probability that a sample value will be equal to the population value, we're going to say that if we're estimating, we basically have no chance of getting exactly the right answer. And I just want to show you that that's the case on this problem. In order for P hat to be 0.40, you would need P hat to be equal to 40% of 187. And 40% of 187 is 74.8. And when you're doing success-failure problems, the number of successes is always a whole number. So you're never going to get an X like 74.8. You might have in your sample 74 females or 75. And if you have that, you will get pretty close to the 0.40. But you're going to be a little over or a little under. You're never going to hit it right on the nose. And so that's the key, right? We're never going to be exactly equal. And that's pretty typical most of the time, that your sample size and your population proportion don't allow you to get an exact right answer from a sample. And again, even when it is possible, it still doesn't happen very often. So we're just going to always say the probability that P hat is equal to P is basically 0. All right, so what we're saying there is if you use a sample, you're not going to get a right answer. So as soon as that happens, we should expect sampling error, so then we should start thinking about how much sampling error. And so one of the things we know about random variables is we expect them to land within 2 standard deviations of their mean. So I want to figure out what is the mean of P hat and what is the standard deviation of P hat. So that's my goal. And so what I'm going to do is I'm going to start out by writing down the mean of X, which is the number of successes. That's from section 5.5, and that would be this, let's see, that would be N times P. And we could write that out for this one. We'll do that in a moment. It turns out that if you're trying to get the mean of the P hats, which is equal to the mean of X over N, because P hat is equal to X over N, then if you're trying to take your old variable and divide it by N, and you want to know what the new mean is, I'm not going to prove this here, but it turns out that it's equal to your old mean divided by N. So when you're trying to get the mean of the P hats, that's the mean of the X over N's. The mean of the X's is NP, divided by that N, and the N's cancel, and we end up getting P. So that's a formula that we're going to want to remember, that the mean of the P hats is equal to P. And if we applied that formula in this case, then the mean of the P hats would be equal to 0.40. And when we're done with this problem doing the by hand work, I'll show you this on the computer, that if we simulate this, that is what happens. But let's look at the standard deviation question. So if we want the standard deviation of the proportion of females in the sample, that sample proportion is p hat. So we go through the same kind of line of reasoning. If you want sigma of p hat, then that is going to be sigma of x over n, because p hat is x over n. And this is a part that needs some proof, but I'm not going to do that here. It turns out that works out to be just the sigma of the x's divided by n. And we know from 5.5 that the sigma of x for an NPQ problem is the square root of n times p times q. And then we would put that over n. And unlike the last time, we can't just cancel the n's because this n is under a square root and this one is not. But we can remedy that by saying that n is equal to the square root of n squared. And if we do that, then both of these are under the square root. So we can now say that's equal to the square root of npq over n squared, putting it all under a single square root. And then we can do some cancellation. So this n right here would cancel one of these n's, but there'd still be an n left over. So we end up with the square root of pq over n. So very similar to our previous formula. So sigma of x, the number of successes, is the square root of npq, but sigma of p hat is the square root of pq over n. So the formulas are almost the same. We just get the n in the bottom instead of the top. So these two formulas right here are summarized for us in this theorem 7.1. If we take a random sample of size n from a population where the proportion of successes is p, then the mean and standard deviation for the possible values of p hat are given by the formulas mu of p hat equals p, and sigma of p hat is equal to the square root of pq over n. So we kind of saw the math on that here. They did ask us what it was specifically for this problem, so let's squeeze that in here real quick. So let's see, the sigma of p hat would be equal to the square root of p 0.4 times q 0.6 over n, which is 187. So sigma of p hat is, and let's have a look at that. So the square root of 0.4 times 0.6 over 187. We want all that in the square root, so you'll get the open parenthesis automatically. Make sure you don't close that until you get all three numbers in there. And then just another reminder, when we're doing standard deviation, we're supposed to do 5 significant digits, but the 0 at the beginning doesn't count as a significant digit on a small number like this. So 3, 5 is 2 digits, and then 8, 2, 4, but the 4 is followed by an 8, so I'll round that up to a 5. All right, and again, we'll run a tech demo in a minute to verify both that this happens and this happens. But first, let's look at the last question on this page, and then we'll go to that tech demo. So we said we had 3 questions on the previous page. What's the mean of the p hats? Seems like we have a formula for that. What's the standard deviation of the p hats? We have a formula for that, and I'll show you on the tech demo that that does work out. But the last question is, what is the approximate shape of the distribution for the proportion of females, or what kind of distribution does p hat have? And I can tell you what we're hoping for. We hope that p hat is normally distributed. Because if p hat is normally distributed, then we can do probabilities using area under a normal curve, which will require z-scores, but we'll know the mean and standard deviation for that variable, so we'll be able to get z-scores. I think this is a reasonable thing to hope for, because we saw it on the tech demo on the previous page with the presidential approval rating. So maybe we'll get it again, but we don't know yet, so we're kind of hoping for it. I'm going to go ahead and show you that tech demo now for this problem, and you'll see that not only do these 2 formulas work out, but we do in fact get a normal distribution or a bell shape for p hat. The thing that we have to deal with is, does that always happen or not? So we'll discuss that after we see the tech demo. Alright, so we just worked out a value of the mean of the p hats, a value of the standard deviation of the p hats, and we have a hope for what shape the p hats will be for this video game player example. Let's simulate that and see how this matches up with our work. So n was 187. The proportion of females that play video games is supposed to be 40%, so we'll set that for the population proportion. Do the run once thing again. Notice we get values kind of close to 0.40, sometimes high, sometimes low. And there's the 3957, real close, right? But if you look at these tick marks, that's where the histogram squares can start building. There's one super close to the 0.40, but not quite there. So it's going to turn out that it's not possible to get that value exactly right. Let me jump straight into the automatic here and let this start running. So we calculated by hand that we thought the mean of the p-hats would be equal to p, which is 0.4. And as we start getting into the thousands of repetitions, it looks like that value is settling in at 0.4. For the standard deviation of the p-hats, we calculated by hand that we thought we would get 0.035825, 0.35, and it looks like it's trying to be an 8, but it's not quite there yet. So we'll let this run. We're getting into almost 100,000 repetitions, so the random variation is starting to squeeze out, but it's still affecting these last few digits of the standard deviation. So while we're letting that run, let's look at what we did in part D, where we said we were hoping that we would end up getting a bell shape for the p-hats. Looks like that hope is confirmed, right? This is a pretty good bell shape for the p-hats that we're getting. So it looks like we've got our shape, and then let's just check back in on the mean of the p-hats. Supposed to be 0.4. We got 400. Well, it's switching on me, right? It's flipping back and forth between 0.4 with a lot of zeros and 0.3999. If we let this run enough, and we're coming up on 1 million repetitions, this would lock in at 0.4, but this last digit's still a little unsettled, so it's bouncing back and forth. But it really seems like that formula is working, that the mean of the p-hats is working out to be 0.4. And then this one takes a little longer to settle down. We calculated 0.35, so 0.35, and then we had 8.25. There's the 8, and this is supposed to be a 2, but notice it's not really settled yet. It's still kind of bouncing around. Right now it seems to be 3s and 4s. I think there I just saw a 2 flash. If we let that run, I think this would become a 2.5 as well. So it really seems like the mean of the p-hats formula is working. The standard deviation of the p-hats formula is working. The shape is the bell shape we hope for. We still need to learn when is this bell shape, when is it not, but it looks like this time it is. Okay, so that demo seems to support what we did by hand, which is a good sign. Alright, so I just showed you the demonstration that kind of verifies that this formula seems to work, this formula seems to work, and that once again we got a bell shape for p-hat, so our hope seems to be confirmed here. So we can go ahead and write that. That was confirmed by the tech demo. But we're not going to have the opportunity every time we're doing a homework problem to confirm the shape of the distribution by a tech demo. So we want to come up with a way where we can just look at the values of n, p, and q and make a determination just based off of that, whether we're going to get a normal distribution for p-hat. And the theorem on the next page gives us that, so let's go ahead and go there and have a look. Alright, so here's the theorem that tells us whether or not p-hat is normally distributed, or at least it tells us conditions for which we can count on p-hat being normally distributed. If we take a random sample of size n from a population where the proportion of successes is p, then if np and nq are both at least 10, then the random variable p-hat will be normally distributed, and then just reminders of the mean formula and the standard deviation formula. But the new piece here that Theorem 7.2 is claiming is that if you check your NP and your NQ, which is just a quick mathematical calculation, if those are both at least 10, you can expect a bell shape for the distribution of p-hat. So I'm going to go ahead and pause here for a moment on the notes, go back to the tech demo, and I just want to show you pictures of the last two, and kind of we'll check the NP, NQ on those, verify that they're bigger than 10, so it makes sense that we'll get a bell. And I'll show you a few cases where either one or both of those is under 10 and how that affects the shape of the distribution of p-hat. And then after that we'll look at an example that takes advantage of this theorem. Alright, so we just looked at Theorem 7.2 that tells us if NP and NQ are both bigger than 10, then we should be getting a bell-shaped distribution for p-hat. This program will draw the histogram for the theoretical values of x, the number of successes, but it turns out that the overall shape for the number of successes x will be very similar to the shape for p hat. So when we look at this graph, you can think of this as telling us what the shape of p hat would look like. So on the problem that we did for the approval rating, we had an n of 614, and we had a value of p, which was 0.522, and over half of 600 should be 300 and something, 320.508, certainly over 10. So there's our NP, and it's bigger than or equal to 10. So now let's try NQ, 614 times 1 minus that, so 0.478. And that's almost half of 614, so that should be near 300 as well, 293. And it's over 10, so NP is over 10, NQ is over 10, and they're both way over 10. And it turns out the further away you're getting from 10, the better bell shape you tend to get. So let's look at that on this simulator. We'll put in the N of 614, put in the P of 0.522, it'll calculate the Q itself, and we get a really nice bell shape for the number of successes, but the proportion of successes would be just as nice of a bell shape. Alright, so it seems to work for the presidential approval rating one. So now let's try it for the one about the gender of video game players. So on that example, we had an N of 187 and a value of P of 0.4. Your worry about NP or NQ being bigger than 10 is always going to be based on the smaller number, but this is over a third of 187, so it's over 60, 74.8, so it's definitely over 10. So if the smaller one is over, then when you switch to the bigger value here, Q, that's going to be even bigger than this number, so certainly bigger than 10. So both of these are over 10. They're both well over 10. We should get a decent bell shape. Let's look at that on this application. So we'll make N 187 and P equal to 0.4. And there's the bell shape we get for the number of successes, so it'd be very similar for the proportion of successes p hat. So as predicted by Theorem 7.2, we're getting a normal distribution for the proportions, sample proportions, when we use an N of 187 and P is 0.4 and Q is 0.6. So far, looks like the theorem is holding up. But the theorem doesn't say that'll always work. It says it'll work if they're both over 10. So let me just show you where we start to run into some problems. Let's play with some different numbers here. What if we took 187 times 0.02? So what if only 2% of video game players were female? Then your value of NP would be under 10 at 0.374. So we might not get a bell shape for that. So let me change this P to 0.02 and see what happens. And on the graph, I think if you look at that, you see it's kind of a right skew. We have a much longer tail on the right than on the left. If you were to draw a bell-shaped curve over the top of that, it's not fitting very well. It's got a whole bunch of extra space here. On some of these, we're getting a lot more of a corner missing than the extra spot there. We'd like those to balance out a little better. Let me show you what that balance looks like when it was bell-shaped. I draw the curve. That curve fits nicer along the tops, and when it cuts through, it tends to cut through kind of in the middle. So the amount that's chopped off is fairly close to the amount of extra we get right there. Alright, so back to that 0.02 again. We have an NP that's 3.74 under 10, and getting rid of that curve, we have a right skewed shape for the histogram. And the same thing ends up if 98% of video game players were female. Then NP is well over 10, so you'd think everything would be fine. But if that was NP was 0.98, then NQ would now be 187 times 0.02, and that one would be under 10. So if either of those falls under 10, you end up, especially if one's over 10, the other's under, you tend to get a skewed shape instead of a bell shape. And if you try and use a bell shape to get area, when the graph doesn't match up with that, your probabilities and areas are going to get messed up. For example, if I click on this square right here, the probability for that square, if you look at the area under the curve, is 0.1915, but the actual probability for that rectangle is 0.2085. So you're off by like 1.5% or so. So we don't like to use a normal curve if we don't really have a normal distribution, and we have kind of a left skew here. And then just a quick comment, if they're both under 10, like let's say we had a sample size of 10 and a p of 0.5. So in this case, NP is 5, and NQ would also be 5, so they're both under 10. We've actually got the bell-shaped in the sense of the symmetry. It's just that it's so kind of big, chunky, stair-steppy that we're kind of worried about these balancing out all the time. They do okay on some of them. It looks like maybe on this one it's maybe not so good. Here maybe we have a problem. So we just don't like it to be too chunky. We like it to smooth out a little, and that requires a bigger N. So if one of the two, NP and NQ, is under 5, you tend to get either left skewed or right skewed. If both of them are under 10, then it might just be too chunky, or it might be too kind of chunked up like this and also not be bell-shaped. Alright, so that gives you a little bit of sense of what's going on with how those numbers match up with graphs. Hopefully that was helpful, and now let's move on and see how we use all this stuff in an example. Alright, so based on what we just saw on that tech demo, it does seem like Theorem 7.2 does hold up. Now I want to show you an example of how we would use that in homework. So let's read the example. Suppose that a random sample of size 365 will be taken from a population where the proportion of data having a given attribute is 0.621. Determine the distribution of the possible values of p hat. So what we want to do is we want to say that p hat has a normal distribution like this. But to be able to say that, we need to check NP and NQ to make sure they're both at least 10. So the first thing we should do is start figuring out NP and Q. It says we have a sample size of 365, so that's N. It says that the proportion having a given attribute is 0.621. That given attribute is what we would think of as a success. So that proportion of successes is the same as the probability of successes, so 0.621. And then we can subtract 1 minus p, or 1 minus 0.621, and we should get 0.379 for the value of q. So there's our n, p, and q. And now we want to check to see if NP and NQ are both at least 10. So just come over here and do that work on the side. So N times P is 365 times 0.621. And a lot of times you can tell in your head that that's over 10. If we were to take 0.5 times 365, that'd be half of this, which would be 180 something. And that's over 10, so certainly when you multiply by something more than half of 365, that's definitely over 10. I'll show it to you on the calculator in a minute, but I think it's good to just think it through. And I don't mind you just doing it in your head. If you can kind of convince yourself it's over 10 without doing the calculation, you could just write this. It should be pretty obvious that it's true, though, if you're not going to show the answer. And then N times Q would be 365 times 0.379. Now this is going to be a smaller answer because we're multiplying by something smaller, but 0.379 is bigger than a third, and a third of 365 would be 120 something, so this would be over 120 something, so certainly over 10. So I'm going to argue, even without my calculator, that both of those are met, but we can double check them real quick. So let's do that. If we have 365 times 0.621, 226, definitely over 10. 365 times 0.379, whoops, 379, 138, definitely over 10. So we've met the requirement of Theorem 7.2 of NP and NQ both being over 10. So what does that tell us? That tells us that p hat will be normally distributed. And that's a good start to an answer, but it's not the whole answer. The problem is there's all kinds of normal distributions. Every different mean and every different standard deviation gives you a different normal distribution. So when you're asked to determine the distribution, they want you to completely determine that. And you've said what kind it is, but you haven't said which one of those normal distributions you have until you identify the mean and standard deviation. So we're going to add on to this. P hat is normally distributed with the mean of the p hats equal to p, and p is 0.621. And the standard deviation of the p hats will be approximately, and let's go do some scratch work on the side for that. So sigma of p hat should be the square root of pq over n. That's the square root of 0.621 times 0.379 over 365. And whatever answer we get there, we'll fill in right there. So let's have a look. The square root of 0.621 times 0.379 over 365. So 0.025393. Remember, this 0 doesn't count as a significant figure at the beginning of a small number, so we have 1, 2, 3, 4, 5 significant figures, which is the minimum. And now let me go put that with the rest of my answers so that this is a complete answer. All right, so they asked us one question, determine the distribution of the possible values of p hat. I would say that has one answer to it, which is p hat is normally distributed with mu of p hat equals 0.621 and sigma of p hat equals 0.025393. So that's the full answer to their question. I will point out that it's typical that when you get this question, it'll say explain. And if that was there, what we have to explain is how did we know it was normally distributed? So then we need this piece right here as well. So I'm going to argue that there's just one answer to that question, but it kind of comes at us in 4 parts. First, we have to look at NP and NQ to see if they're both over 10. And if they are, then we know that p hat is normally distributed, which is the main answer to the question, what kind of distribution does it have? But then we want to narrow it down to just a single unique distribution. So we need to say what the mean is and what the standard deviation is. So when you get this question, you need to make sure you're answering all 4 of those parts. What's NP and NQ? If they're bigger than 10, p hat is normal. And then use our formulas from this theorem and the previous one to come up with the mean and standard deviation. Just one answer, but 4 things that you need to think about to make sure you've completely answered the question. All right, so why do we care about the distribution of p hat? Well, if we know what the distribution of p hat is, it does allow us to start answering probability questions about that. On the next few pages after this one, we'll start seeing how that relates to sampling error. For now, we're just going to practice doing a probability for a p hat. So determine the probability that p hat is between 0.60 and 0.70, inclusive on one side, not on the other. All right, so p hat is a random variable, and it has a normal distribution. Anytime you're trying to find a probability for a normal distribution, you should do that using area under a normal curve. It doesn't matter if the variable is called x or y or q or z or p hat. So first step would be to draw a bell-shaped curve. We should label the spot under the peak as the mean, and the mean of p hat is 0.621. I think it'd probably actually be a good idea to write right here too that this is for p hat. And then put our boundaries on the picture. 0.60 is to the left, 0.70 is to the right. Just a reminder that when we're doing normal distribution work, we don't worry about whether we have a less than or equal or just a less than. We just use those boundaries as they are. And we want the probability of landing in between, which would be this area in between. So this question at this point is really just a chapter 6 question. It might feel like something new because of the p hat, but if you're trying to find the area under a normal curve and you've drawn your sketch, then the next thing to do would be to get z-scores. So let's find a z for this one. So z would be the boundary value, 0.60, minus the mean of the p hats, 0.621, and then divide that by the standard deviation of the p hats, which is right there. So I'll write that number down there, 0.025393. And we'll put that one in the calculator, but we'll also want to get a z for this one, so I'll call this one z1. And z2 would be the same thing, just with a 0.70 instead. but the mean of the p-hats is the same, the standard deviation of the p-hats is the same. And I just noticed I didn't put the 3 here, so we'll slot that on there. And then we'll go ahead and get both of those one at a time, but it's kind of useful to be thinking of doing them at the same time because the calculations are so similar. So let's do this one right here first. So parentheses around the numerator of z-scores all the time. So there's our subtraction, and divide by 0.025393. So there's my first z-score. We always put exactly 3 decimal places on z's, so that'll be negative 0.827. And then to do the other one that's under the calculator, that has the boundary of 70, so I'm just going to do second enter to pull up the last calculation, change that 60 to a 70, and press enter again. Alright, so the one on the right is 3.111, and the one on the left was negative 0.827. So once you have your z-scores, you're ready to get area, which is probability. So whatever this area is, that's the probability, but I can find that area by using normal CDF from the left z-score boundary, negative 0.827, to the right boundary, 3.111. Okay, so we'll do that on the calculator. I'm just going to give a quick guess. If the right z-score is really at 3.111, that means it's basically all the way out to the edge of the visible part of the graph. So I have the whole 0.5 on the right-hand side, basically. And on the left, going almost 1 standard deviation should pick up quite a bit. If I went over to negative 0.674, that's the quartile value, that'd be another 25%. This is even more. So maybe an answer around 80%. Let's have a look. So distribution function, normal CDF from negative 0.827 to positive 3.111. And I thought it'd be around 80%, and I'm getting something super close to that, 0.7949. And I'm going to box my answer for 2 reasons. One, because I have the scribble, so this will clarify that a little bit. But also we got work kind of all over the place here, and we want to make sure make it very clear what part of all this work was the answer to that question. And there it is. So this should feel a lot like chapter 6. We just have a different variable name, p-hat, that we're using, but we're still doing area under normal curves, so we get z-scores, then we use normal CDF. All right, so now we're starting to see how we're taking advantage of the normal distribution, and so let's continue on to see what else we can do with these sample proportions on the next few pages.